What's up, math people? We are back again with another one. Alright, so check it out. My son is asleep, so I'm kind of hype, okay? He's sleeping in the other room. Alright, so this time, coming from the calculus standpoint, Cal 1, we're talking about applied optimization. Alright, optimization is the action of making the best or most effective use of a situation or resource. Alright, so with applied optimization, I'm all about knowing some shortcuts. So right off bat, I'm gonna go ahead and toss up a quick little shortcut. All right. So applied optimization. Number one, get the desired formula, derive it, derive that formula, set equal to 0, and solve for the variable. That, my friends, is applied optimization in a nutshell. All right. So let's jump into an example so I can prove to you my simple truth. Oh, I ain't mean to do that. I try to be real smooth by swiping the screen. All right, but let's go on to the next. All right, so this example says, suppose. All right, let me get this guy ready to be marked up. Suppose that the cost is given in the above stated function. This is the cost of manufacturing X items. Find the production level that will minimize the average cost per item of making X items. The thing about applied optimization is background knowledge, man. Like, if the background knowledge is missing on some of these formulas, you'll be completely lost. Right here, we have a request for average cost. Now, average cost, the cost function is given. Average cost is equal to, it's called C bar of X, and is equal to the cost function divided by the items. So the average cost is x squared minus 18x plus 30,000. We divided each term in the cost function by x. Alright. Now it said it wants us to minimize average cost. Alright, so let's put my theory to work. We we have a we have acquired the desired function. The next thing I told you to do is to derive the desired function. So we're going to derive the desired function. The derivative of x squared minus 18x plus 30,000 is 2x minus 18. Then we said set the desired function equal to, set that derivative to 0. 2x minus 18 equals 0. And then we said solve it. Solve for the variable. 2x equal 18, x equal 9 items, cause x represented items. So with that being said, going through what we asked for, 9 items will minimize the average cost. Still don't believe me? Let's move on to the next and try another example. Alright. Alright, so we have Find the smallest perimeter and the dimensions for a rectangle with an area of 196 square inches. The smallest perimeter for a rectangle. Again, applied optimization problems is all about background. Alright, so we have a rectangle. All about your background info. Let's say that this is the width, this is the length. The perimeter for a rectangle is calculated. We have length happening twice plus the width happening twice. But I want you to notice it slides a little. It'll slide a little information into a problem to jug your memory, to cause you to think a little bit. Why did it slide in area? Well, we're talking about rectangles, so let's go ahead and again pulling out background knowledge. Go ahead and put in the area of a rectangle. The area of a rectangle is equal to length times the width. Alright, but it said that that area is equal to 196 square inches. Oh, now we can see that's why we pulled it in. Up here with the perimeter, we're dealing with two variables, L and W. Perimeter consists of L and W. If we go ahead and solve for one of those variables from the area formula, we can simply say, okay, width is equal to 196 over L. We'll take that and put it into our perimeter formula. So we have 2L plus 2W, and I'm just gonna do this right here. Change this color, let you see that W is 196 over L. Just put it in red, 196 over L. We've changed nothing. All we did was substitute in. Alright, so now we have one variable that we're dealing with. Since we're dealing with one variable, let's go ahead and simplify. Perimeter is equal to 2L plus 196 times 2. 400 minus, what's that? 400 minus 8. So that would be 392 over L. We have our desired formula. We want to find the smallest perimeter. We want to optimize this problem right here on perimeter. So now we're going to say P prime. We get the desired formula, derive it. That becomes 2 minus 392 over L squared. Then we said set that derivative equal to 0 and solve for the variable. Solving for the variable, we have 2 is equal to 392 over L squared. And I'm just trying to grab a calculator right quick, team. Alright, swing this on around. We have L squared is equal to 392 divided by 2. L squared is equal to 196. Appreciate y'all. And then when we take the square root of 196, we get L is equal to 14. So the length is equal to 14 inches. And the width you'll just plug it back in. width is 196 over the length, which is 14. So the width is also 14 inches. The problem asked us to find the perimeter. So we'll plug all of that back into our initial perimeter problem, our formula. We have P equals 2 times 14 plus 2 times 14, 28 plus 28. That would give us 56 inches would be the smallest perimeter that we could obtain. Still don't believe me? Man, y'all drive a hard bargain. Alright, I got one last example I'm gonna push off on you. And I'm like, if you don't believe me after this, it's a wrap. Okay? Alright. So let's go ahead and jump in one last time. One last example. Again, when doing applied optimization problems, it's all about background knowledge. Make sure your background knowledge is in flow, and then let's see, you get the desired formula. Next, you derive the desired formula. Set it equal to 0. Solve for the variable. All right. It says here a rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single strand electric fence. With 1,700 meters of wire at your disposal, what is the largest area you can enclose and what are its dimensions? Okay. Alright, so that problem asked us for two things. The largest area we can enclose, and the fence's dimensions. Alright, so it said we got a farmland fence and it's bounded by a river on one side. Alright, so here go my river. Alright, farmland. Let's go ahead and make this farmland nice and green. Alright, and make my river, put a little bit more oomph on my river. Yeah, got that water flowing through. You know what I'm saying? Alright, so let's go ahead and swing this back. And it said with 17 meters of wire, alright, at your disposal. So let's say this represents the length, this represents the width, and right now my width is a little bit too thick. Alright, now we have the perimeter for that wire would be 2L plus W. Alright, we say 2L plus W this time because only 3 sides of the fence is going to get wire. Only 3 borders are going to get wire. The other side is going to be bordered by the river. Alright, now we have 1,700 meters of wire is what's going to go around that. That would be the total perimeter. Alright, it said what's the largest area? Again, we're talking about the area of a rectangle. The area of a rectangle area is equal to length times width. Alright, and using this information on the right hand side of your screen, we're going to solve for one of those variables. We'll go ahead and solve for width. So width is equal to 1,700 minus 2L. We'll take that and take that information for width and plug it into your area formula. So we have A equals length times width, which is 1,700 minus 2L. Alright. A equals 1,700 L minus 2L squared. We have our desired formula. We have one variable. Now we want to maximize area. since we maximize the area, we're going to go ahead and take the derivative of this. We have 1700 minus 4L. Next thing we do, we derive it, take that derivative, set it equal to 0, and solve for the variable. Alright, so we have 1700 equals 4L. Alright, so 1700 divided by 4, that would tell us that the length is 425 meters. 425 meters represents the length. Alright, so if 425 meters represent the length, how many meters represents the width? You just go ahead and plug that information back up top. We have 1700 minus 2 times 425 equals the width. 1700 minus 2 times 425 will give us 850. 850 meters. Units are important. Alright, so we got the desired units. We got the desired what the problem is. We got the dimensions. The length is 425 meters. Width is 850 meters. And the area, the maximum area, you take those and you plug them into your area formula. 425 meters times 850 meters gives you 361,250 square meters. You got everything right there, son. Like I tell you, it's all about that background info. All about that background info. All your answers right there. Alright. Okay, we got time for one last example. Alright. So let's toss a curveball at you to pull some information from your pre-cal background. Alright. Let's say you have a triangle with 2 legs of length 10 feet for each. And we want to find the angle theta between those that will maximize the triangle's area. Alright, so background knowledge right here. Alright, so draw your triangle. These legs right here are both 10 feet. We wanted to know the angle theta that will maximize the area of this triangle. Alright, so there's some area formulas for triangles. Alright, but you got to be able to pull that stuff up. You have to have it on ready. We know that one area for a triangle is K equals 1/2 AB sine theta. And that have to be a side angle side. That angle theta has to be between those legs like we're given. And we're given everything we need right there. So off bat we immediately have the desired formula. So once we get the desired formula, we plug in the info, 1/2 times sine theta. Next thing we do is derive it. K equals, this will be 10 cosine theta. Set the derivative equal to 0 and solve for theta. Cosine theta equals 0. Theta equals cosine inverse of 0. That's saying to me what angle on the unit circle gives me an x value of 0, and that would be at pi over 2. Easy enough. Hey, that's another math one. Calculus 1. We are out.